Okay, now we'll go ahead and get started. I did want to call attention to a couple things. One, I did successfully record, as best I can tell, lecture Tuesday. So just as a heads up, from the Canvas course under modules, if you go to Unit 1 recordings, you'll see that link. As best I can tell, it captured my voice and it also captured annotations on the screen. So if there's anything that you missed or you like, I want to double back to and rewatch that, figure it out, you've got links to it, which you could also find in YouTube if I don't update here, theoretically. Which then takes us to our lecture 3. I've seen a couple questions come through on the IUPAC. There's been a couple on IUPAC stuff for naming, so I figured I would address these common names that keep popping up. Oh, come on. What? The recordings, the lecture recordings, when you go into modules, it should be one of the very first modules. Technically, it's the third one right now. It says live lecture recordings, Unit 1 recordings. And then you'll see Unit 2, 3, 4 pop up when we actually have those. Logistically, do you guys want these module things? Oh, that one's for faculty. You don't care about it. The student resources, should I move that to the bottom so it's not in the way? Okay. I will go ahead and get that moved to the bottom. In fact, I can do that right now because it's easy. I'll get that moved out of the way so that you don't see it. Click. But then back to the kind of IUPAC stuff, because you will see these things kind of pop up. We talked about that ISO a little bit, though I don't think I provided, at least for my sake, enough context behind that ISO group. So when we're talking about these common name pieces, typically we're using them in a larger structure. So we have some kind of extended structure, bunch of bonds on it, whatever it is, and then you would have hanging off of it your substituent. So there's a couple ways you could represent that. Here we could represent it with just showing it as different colors. Okay, typically what you'll see, and I believe it is actually done this way in the in one of the specs quizzes, is you'll see your structure like in red, but then you'll see a little squiggly line underneath it. That squiggly line just represents the structure continues on. Really the only thing you're caring about is what that red thing is. Okay, so when we first look at this, the idea is that you would see, kind of for lack of a better description, okay, you kind of have like this fishtail hanging out, right? That's a fishtail. Fishtail's green. Okay, and if you have that fishtail shape, that's your ISO name. Okay, so we see that fishtail in red, so we go, oh, this is ISO. Well, ISO what? ISO is just referring to that fishtail-ish kind of description. So we would need to define a little bit more information about it, like the number of carbons. Well, how many carbons do we have within that ISO shape? 3. So that gets called isopropyl. Okay. There are other common names that can kind of pop up or get in the way, but we'll start with kind of the roots for our ISO. We could go through and do this. Do you see the fishtail? Yeah, so it is a fishtail, so we should be using ISO. Should we be calling it isopropyl? Okay. The name is in reference to the substituent, so that's everything that we've kind of identified within blue in this case. That's not 3 carbons now, that's 4 carbons. So we need to call that isobutyl, because but is our root for 4 carbons. Okay. I forgot I can slide things around, and I just deleted everything, so we'll just pretend you knew that what was going on there, and we'll go to a new potential name. Here we go. What do you see? What do you think we'd name this? So for sure, do you see the fishtail? Yes, so we should be calling this ISO. Okay. Now, how many total carbons are in it? So there's 1, 2, 3, 4, 5, 6, 7. There's 8. So I'd call this iso octal because it's a substituent. And if you go through and look at your textbook and try and find this, you'd be like, well, I don't see isooctals showing up anywhere. Why not? What are we trying to name? The substituent. To get isooctal, what does that say about the main chain? It has to be way longer. And not just longer like it's 9 carbons. It has to be longer so that when you count coming in either from the left and up versus from the right and up, that this, your total length, is still longer than either of those. So you'd be looking at a really long main chain, right? Okay, so we typically don't see these isooctal kind of names show up, but theoretically they're possible. Does that make sense? Okay. So let's delete all that because now that we understand our isos, we got to make it more difficult with something else. So here's a little chain. Don't stress about the number of carbons in said chain. Pen. Give me colors. Fine. I don't. Oh, it just deleted everything. Now everything's back. Can I get a pen? There's black. There's my main chain. Give me red. Do we have the fishtail? Okay, and so for people looking at this and saying, well, we've got a fishtail, we have the fishtail right here, right? Well, no, you don't have the fishtail right there because you also have this dingus going on it. Okay, so this is a mutated fishtail. There is no mutated iso. That doesn't exist. Okay, so we have to come up with a new naming system for this. I swear there's an undo. Maybe I just do it. Oh, that just deleted everything. So, I mean, that's undid. Okay, so how do I go through and name this one? Well, how many carbons is it? Let's start with that. 4. Okay. And for people being like, well, isn't it 1, 2, 3 carbons, and then there's a methyl group at the 1? That's awesome. That's IUPAC. But again, we're talking about common names, and we're talking about stupid systems, not normal systems. Okay. So how could we reference this? So yes, there's 4 total carbons. We're looking at a butyl. But now the question becomes is how can we be clear about where this is located? Okay, and for the record, I do not make the rules. Okay, I don't even want to talk about these rules because I think they're dumb. Okay, but what we're going to do is look at where the butyl substituent connects to the main chain. And when I look at that butyl substituent, it is connected to how many carbons? 2. What about 3? We don't care about the main chain, we only care about the substituent. So it is connected to 2 carbons. One of the things that is going to come up later in the semester is that when we talk about, typically we'll talk about it as carbons, as carbocations, we would go through and we could label that type of carbocation as being tertiary. And I could label a carbocation as secondary. What do you think this last one might be? Primary. What are we counting out? The amount of carbons connected. So primary 1, secondary 2, tertiary 3. So when we go back to this naming system here, we looked at our carbon where our butyl chain was connected, and it's connected at a carbon that would give me a secondary carbon, which means I'm going to call this. Okay, so some people are going with the correct answer, probably because they've done a little bit of reading on it. And other people go, oh, that makes sense. Secondary butyl. Secondary is, of course, too many syllables, so we call it sec-butyl. Okay, so that's now what that substituent would be called. Okay, fun little story, because we know how much I love nomenclature. If we looked back at the ISO substituent, right, up here. This is isopropyl. When you go through to alphabetize, put your substituents in alphabetical order in your name, isopropyl is sorted based off of what letter? Isopropyl is sorted based off of I, because it's the first letter in the thing. That makes perfect sense, right? What is sec-butyl sorted based off of? B. B because. Okay? And officially, I drew this out a little bit wrong because there's a dash there. Maybe that's why you don't count the sec as part of it. But that substituent is now known as sec-butyl. So when you put it into the list, you would sort it alphabetically based off of the B, but you would call it sec-butyl. This structure here, why are we not calling it isobutyl? Because I don't have an iso. Iso is that 3-carbon fishtail. I don't have a 3-carbon fishtail. I have a 3-carbon fishtail with a mutation on it. Okay, kind of like me when I was born. Okay, I had a little dingus hanging off my ear. They cut it off. Okay, allegedly true story if you believe my parents. Okay, that's not an iso anymore. That's a mutated shape. Because it's a mutated shape, we call it a different name. When would we call it isobutyl? What do we need to do? I need a fishtail, but I need 4 carbons. So if I put a fishtail immediately there, that's isopropyl. That's isobutyl. Okay? So it's about where it's connecting. You're like, well, doesn't it have a little dingus off of that too? But yeah, that's where it's connecting to the main chain. It still has that iso section hanging off. There's my iso fishtail. It's just the rest of the tail got longer. Okay? What if I add a carbon? And I know that happened fast. Let me delete everything else. So our isobutyl, I added a carbon. There's no longer 4 carbons. So what should I call that? You were mouthing it. So pent, there's 5 carbons. Where is that 5-carbon chain connected? It's connected to a carbon that has 2 carbons connected to it. So my name becomes sec-pentyl. Neat. Or not. I would say not. Okay? And if that weren't bad enough, what we're talking about is how we could rearrange each of these carbons and generate new pieces. What happens if I go back to my drawing here? And now I do that. Okay? And now you'd be like, well, don't I have the iso again? Well, you have the iso again, but now where it's connecting at the fishtail, it has another fishtail. So this is super mutated. Like this doesn't work. Okay? This is growing another ear off my ear. Like that doesn't count. Okay? Can I call it sec? Well, look at the carbon where it connects to the main chain, that center spot. Okay? Is that center carbon? We'll make it a big red dot. Is that center carbon secondary? Is it only connected to 2 carbons in the substituent? No. How many is it connected to? 3. So I can't call it secondary or sec-butyl. I'll have to call it tertiary. Bah, too many syllables. Cool. I'll call it tert. Okay. Just like the secondary, I need to include that stupid little dash. So it's tert dash. Now how many carbons have I shown? So tert butyl. That's a while. So that substituent is now referred to as a tert butyl. Well, just like we did with the isobutyl or the iso and the sec position, could I do this even more? Of course, why not? So now what should I call it? Why did we call it tert? Where it was connected to the main chain was connected to 3 carbons. Is this connected to 3 carbons where it connects to the main chain? No. So I can't call it tert anymore. Calling it just pentyl does, yeah, pentyl doesn't make sense because it has 5 carbons, but they're not a straight chain. How would you name this? Fun story. I had no clue. And one of you lucky few pulled this structure in the multiple choice for how do you name this? I was like, I have no clue how I would answer that question, short of just looking it up. Okay? And I believe, and I could be wrong. Again, it's nomenclature, so everything with a grain of salt. I believe this one is called neopentyl. And if you want to know why, you talk to somebody else. I have no clue. Okay? So when we're looking at those common names, there is a logic system behind it, but just because there is a logic system doesn't mean that logic makes any sense.
So according to Google, the prefix neo is 2-methyl groups on the second to last carbon.
Okay. You can definitely use Google for nomenclature if you want. Yeah, that's useless information. But there we go. It's 2 methyl groups on the 2 methyl groups on the second. Hey, oh my God. So if that's the rule, if I do this, what do we neo? Why is that prefix escaping me? That's 6 carbons, right? 4, 5, 6. So that's neohexyl. I don't know.
You said the tert you use when there's 3 carbons connected directly to the chain, right?
Directly connected to your
Like the backbone.
backbone. Yep. Okay. And that one I'm actually going to pull back up and talk a little bit more about because we will see that one again. So if we go through and go back to this, we would call this tert butyl, right? Where did the tert come from? Where did the tert come from? The word tertiary. It's referencing how many carbons are connected to it. Okay, so that's great. Okay, so we're saying that carbon is connected to 3 other carbons in our substituent. So that's where tert came from, but we were lazy and we said tertiary was too many syllables. But we're lazy. Doesn't tert have too many letters? Yeah, which means we'll oftentimes see tert butyl drop into becoming T-butyl. Okay? So the T-butyl as a quote unquote substituent will absolutely come back later in the semester. We use that as a, we don't use T-butyl, but we use T-but oxide as a chemical reagent. So that structure is of critical importance. So T-butoxide. Okay, you're like, well, I don't know how to name that because it's negatively charged. You're right. You don't need to worry about it. We tell you that that's what it's called and don't stress. Okay, so you will hear reference to T-butoxide. It's a critical reagent that we need to understand and use and manipulate later on. We don't name it IUPAC because then it would be 1,1-dimethyl ethyl oxide, and that's just dumb. So we call it by its common name. Okay, the ISO name does show up every so often, but it really only shows up in one place that you've already aware of. How do you remove fingernail polish? Isopropyl alcohol or isopropanol. That's where you'll hear reference to de-iso again. So these common names do kind of make appearances, but they're usually making appearances in places where the context tells you what it is, and then you just kind of memorize it at that point. Devoting any time to actually figuring out sec, but, all of that probably isn't worth your time.
And so IUPAC is like the priority one with like the huge list, and then this is common names?
This is a common names. And unfortunately, the common names for our substituents will get slotted into IUPAC. Because remember, when we're looking at the names, you've got substituents on a main chain. So you can go through and name it fully IUPAC, or you could double back and say, well, I'm going to use a split version, and I'm going to use common names and IUPAC names. Or you can just throw it all out and you just entirely make up a name.
And then they were saying, like, for the specs quiz, people were getting those. Is it specified if you have to use common or IUPAC?
You will know because I think it's multiple choice. It draws a structure and says, what's the name of this substituent? And it's isopropyl, sec-butyl, sec-propyl. I don't think there's sec-propyl or propyl. So sec-butyl, sec-pentyl, tert-butyl, neopentyl. There's a list, I think, of like 10. Okay. And when you get that, I believe that particular specs quiz starts in big red letters. Do the first two parts, do your best guess on the last part, because if your best guess gets you right, we don't care. Right? You got full credit. If it gets you wrong, I need to know, so you send me a message and I go in and just give you credit. And then I laugh at which one you got pulled, like neopentyl. Which, for the record, I'm not laughing at you, I'm laughing that the question was asked. Make sense? Okay. So the next thing I've got on my list is more for me, I would argue, than y'all, is resonance and molecular orbital theory. Everybody's favorite two topics. You love resonance so much, let's combine it with molecular orbital theory and just make it a lovely mess. Okay. Before I just run rampant with whatever I want to talk about, what do you have questions on? Or you unleash the beast. Okay.
How do we, I guess we could do, like, there was an example, C2H4, like, with one of them. And then when it gets to the bonding and electrical bonding, how do you know how many sigma pi bonds
Okay. So if we're going to look at bonding and anti-bonding, so this is not a bad introduction into this. This sets us up for looking at molecular orbital theory. We did a whirlwind run through on this on Tuesday. Maybe I kept 10% of the class with me. I hope it's more than that, but if I'm going to be honest, it was probably 10% or less. Okay, it's because we had a large build-up through that. So let's tackle the same question, but instead of going through the background theory behind it, we're going to assume you've got some of that background theory, and we're just going to look at it from the beginning. Okay, so C2H4, if I'm going to understand anything about molecular orbitals, what should I be looking at? I should be looking at a molecule. Right now, I don't have a molecule. What I have is just a formula. So what I need to do is convert that into a Lewis structure or a molecule. Let's see if I can do it. Oh, I was already going to do it wrong. God damn it. Okay. That's what happens when you try and predict. Okay, we have C2H4. Okay, when we're talking about the molecular orbitals, really what we're trying to drill into is what's happening in each of the bonds. Why do you think I would color all of these red bonds the same, but then differentiate green and black? So if we're running sigma versus pi, that's not a bad guess. I would argue that could be black versus green. What kind of bond is the red one? Sigma or pi? Sigma. So doesn't that overlap with one of the green or the black ones? And yet I chose a different color. Why am I choosing different colors? It's not nothing to do about motion necessarily. What's that?
The domains.
Okay, so the black and green ones are connected between carbons, whereas the red ones are connected between hydrogens. So what you're telling me is the red one is different from the green and the black because it's connected to a different atom. Yes, that's it. Why show all the other ones as red? Like that explains one of them being red. Why are the other three also red? They're all the exact same type. So once I've defined what one of the red one is, the other three are the same. So I don't have to worry about them. So this simplifies my approach and how I'm going to go through and look at things, because I'm looking for patterns to find where things are different, then only discuss the differences, not look at all the similarities. Okay, make sense? So let's start with calling it simple is the wrong way, simplest of our comparisons. Okay, that doesn't make it simple. It's the simplest. So let's look at a red bond between the hydrogen and the carbon. Okay, what does that bond represent? Not yet, but yes. What does that bond represent? Simplest level. Electrons, and in particular, 2 electrons, right? Every line represents 2 electrons. That's what Lewis structure means. Okay, those 2 electrons are existing between those atoms. Well, you took 151. Where do electrons exist? They don't exist in shells. Shells would be a description of those electrons. They exist in orbitals. And we could define all the different characteristics of said orbital that would include shells. Okay? So when we look at a hydrogen atom, the electron that it has is located in an orbital. When I look at a carbon atom, the electrons it has are located in orbitals. When I go to a molecule, can I just use the atomic orbitals to explain what I'm seeing in the molecule? Okay, and that's where we run into a little bit of a dilemma. Consider the carbon, because the carbon's going to be the easiest one. The hydrogen, yes, the hydrogen atom orbital can be used to explain because it only has one. Can the carbon? How many groups of electrons are around that carbon? Okay, and that can be a hard question, particularly depending on how you learned Lewis structure, which is why I would recommend looking at the optional Lewis structure video. There are 3 groups of electrons around that carbon. And because it has 3 groups of electrons, we know that its shape is okay. So for the sake of the recording, we're hearing some SP. Well, one of those answers was correct, and one of them you actually didn't say when I started to repeat that. Which of those 3 answers is actually starting to get on the right path? Trigonal. Okay. Hybridization. I didn't ask that. I asked for the shape. Tetrahedral. Nope, it's not tetrahedral because tetrahedral is 4 groups. Okay. So trigonal what? Trigonal planar, not pyramidal planar. So that's our 3 groups of electrons all trying to splay as far away from each other as possible, and that turns into effectively, oh, my screen flipped upside. Okay, our peace sign, more or less, right? Or Mercedes, whichever you want to pick. Oh, peace is this, isn't it? So it's Mercedes. Okay. So now what would be the next question that I might ask? What's the bond angle? Okay, this is 120. Okay, you can do that by pulling back your geometry skills, okay, or by having memorized it. Geometry skills, if I start here and I go all the way around, how far have I gone? 360 degrees. How many sections do I have? Divided by 3 gets me 120. That sets me up, okay? Theoretically, you could do the same thing with tetrahedral structures to get 109.5. That's a little bit more advanced with the geometry, okay? Or is it trigon? Whatever. You could do it, okay? Or you just memorize, okay? So it's 120. Why does that become important? Well, if I use the atomic orbitals on carbon to explain the bonding pattern, which atomic orbitals are going to get me 120 degrees away from each other? if I'm looking at carbon, which atomic orbitals on carbon get me 120 degrees? So the instant you say hydrogen, no. Okay, sp2. Is sp2 an atomic orbital? No. What are my atomic orbitals for carbon? S and p. That's it. Do any of those orbitals come to 120 degrees? Okay, so go back and review. Take a look at your p orbitals. They're on the XYZ axis. The angle between them is 90 degrees, not 120, which means the atomic orbitals cannot be directly used to explain the bonding patterns that we see in reality. So we have to come up with a different system. Okay? The full-on system is we bust out a supercomputer and we look at the linear combination of atomic orbitals and explain all the bonding patterns that go behind that. And it's wicked and it's cool and it's neat and it's fascinating and it's way beyond the level of this class. And I doubt anybody in this class will ever understand or see it. Okay? So instead, we had to come up with something else that approximated what we would see. That something else was hybridization theory. Okay? So if I need 3 groups of electrons, okay, I need 3 molecular orbitals to allow me to align this. Well, carbon has 4 atomic orbitals, and since I can't destroy that matter, what I'm going to do is take 3 of those atomic orbitals, and I'm going to say they no longer exist. I'm going to mash them together to create a new orbital. That new orbital is my hybridization. So when I go through and look at those carbons, what orbitals do those carbons manifest? There is no S because it's been hybridized. Okay? If you just take all the p orbitals, you're now leaving the s orbital, the lowest energy, unhybridized. If we're going to hybridize, we always start with the lowest energy. So S has to be involved in a hybrid orbital. What hybrid orbitals is my carbon going to have? And for the people that shouted out what the hybridization was, this is your opportunity to shout it out again. sp2. Cool. What other orbital do I have? Cool. A leftover p orbital, which I'm going to suspiciously draw away over here. Okay, I've talked nothing about which of these orbitals has electrons. Okay, so we don't care about that. How many atomic orbitals did I start with? How many atomic orbitals did we start with carbon? So I did hear an answer 2, which was confusing me for a second, but I just latched onto it. You were like S and P, that's 2. That's 2 types of orbitals. How many orbitals? 4, because the p type subdivides into 3 orbitals. So when I look at carbon, it has 4 atomic orbitals. And if I'm going to go through and hybridize, those orbitals effectively represent energy. So if I'm going to mash all that energy around and create new things, can I destroy that energy? Nope, it has to still exist. Which means when I go through and do my hybridization, how many orbitals had I better draw or identify? Rhymes with door. 4, I need 4. You gave me 2. What other orbitals does the carbon have? sp2 and sp2. That's what it means. People tend to solely classify hybridization and now say it's a single thing. No, it's not a single thing. Okay? There are 3 sp2 orbitals, just like there's 3 p orbitals. Why do I have 3 sp2s? Well, how many atomic orbitals did I put into that? An s and 2 p's. That's 3 atomic orbitals in. I get 3 molecular orbitals out, or new atomic orbitals. Okay? And the special thing with this is that if we looked at the overlap, constructive, deconstructive overlap of all of those orbitals with each other, what we would find is they would align in a way that generates a 120-degree bond angle. Ta-da! Magic. Okay? So now we can go through and use that information. So let's take a look at one of those red bonds. Okay, in that red bond, we've got a hydrogen. What orbital is the hydrogen bringing in? An s orbital. Okay, so we could go through and be real fancy and draw a sphere because we know s orbitals look like spheres. What orbital is the carbon bringing in? 3 p's. There's nope, I only have 1 p. There's my list. Okay, since I'm making a single bond, my single bonds are going to become sigma bonds because they involve s-type orbitals. Which of those 4 orbitals is an s-type orbital? sp2, which means the type of orbital my carbon is bringing in is going to be an sp2. Okay, I could get real fancy and start to show shading and not shading behind these if I really wanted to, but these are effectively my atomic orbitals coming in. Okay, as they get close enough to each other, what happens? Those orbitals will now overlap. Okay, and they can now overlap in a constructive fashion or a destructive fashion. Okay, our sp hybrid already has what's known as a node in it, a space, a line where our electrons can exist. We don't see that in our s orbital. Okay, those nodes are referring to the phase. The s orbital is all uniform phase. It will either be all positive or all negative. When? All the time. But it's constant. It's going to happen that way. Okay? Since it's happening all the time, we're going to pick a static picture. We're going to pick a static picture where it's positive. So we'll say shading is positive. If I bring those two close to each other in the overlap, and they're both positive, what happens to the amplitude of the wave? It gets bigger. So now what we're saying is when we look at, let's add a nucleus in these, just a little bit of extra information, is that I'm going to get a big population of electrons, and then this tiny little node thing out here. This will all be shaded in, and then what I'll see is the node for the nucleus of my carbon and the node or the nucleus for my hydrogen. Note the hydrogen is inside this. Why? Because of the shape of those orbitals, how they align. Okay, that's what my picture shows. In this picture, what does it show about the electron density of the carbon or in between the atoms? Do I have a lot of orbital space? Yeah, there's space there that's shaded in. Yeah, I have a lot of space, which means the electrons can exist where? Between the atoms. Okay, and since it can exist in a larger space now, that larger space is lower in energy. Okay, so that's why I drew it lower than my atomic orbitals. Okay, and it's existing in between the space, which would suggest this would look like a bond. Okay, what kind of bond do I want to call this? Well, it's our first one, so theoretically we don't have to name it, but there's more, so we're going to have to name it. Okay, we want to pick a name that helps us understand where it's coming from. It's coming from s-type orbitals because they're s-type orbitals. We want to call it something that begins with S. And sigma happened to be what was picked. So we can call this a sigma interaction. Okay, if we want to get more specific, we could call it a sigma bonding orbital. Okay? Questions? Because here's where it gets wild, in my opinion. Okay. Go ahead, please.
For the very first thing you said atomic orbitals cannot be used to explain the 3D atomic structure.
Yes. Okay. What did I say about that s orbital? I know, lots of stuff. I said it was both positive and negative simultaneously. So it is either shaded or unshaded simultaneously. We looked at the case where it was shaded. What if it happened to come into this alignment where it was unshaded? Now when those two lobes interact with each other, what's going to happen to the wave? It's going to cancel. So this is not going to look like that bottom picture anymore. It's got to look like something different. Okay? And because I don't have anywhere space, I'm just going to draw it above, which may, turn out to be useful. So there's my nuclei, and now what happens? The space in between, they overlapped, where now the electrons can't exist. So what's going to happen in between is I'm going to generate the same thing I generated in that sp2. I'm going to generate what's known as a node. The electron can't exist there. So there's no coloring, shading, phase, image in that space. Okay? And then what happens on the other parts? Well, my electrons are now going to be effectively larger on that outside, relatively. And then with the other one, we're going to get something similar. We're going to get that larger on the outside and then in there. Okay? And we'll get those nodes. Each of those nodes, note what happens is we get a change in the phasing. Right? I started unshaded, node became shaded, another node, unshaded. Everybody seeing that? This is still a sigma interaction. So it is still a molecular orbital. It exists. Just like for hydrogen, I have a 7s orbital. It's there. Okay, so it exists. I want to come up with a name for it. Why do I want a name? Do you like drawing these cartoons? Okay. Cartoons are probably a pain to draw, so maybe we come up with a name so we don't have to draw cartoons. Okay. What name do we want to use? Well, what kind of interaction was it? It was sigma. So I want to call it sigma. Oops. But I don't want to call it the same sigma as I had down here because they're different interactions, right? Okay. Well, I don't have electrons between the atoms, so I'm going to call this not a bond. But I can't call it not a bond because not a bond is those two atoms never talk to each other. They are talking to each other, so I can't use not a bond. This is where we invent a new negative term, and that's our antibond. Okay? I want to make sure that antibond translates into my symbol, so it's going to be a sigma, and I now need to add some information to it so that I denote that that is an antibond. The way I do that is with the asterisk. Okay? So doubling back to the question that was asked, how do we deal with all these bonds and antibonds? When I looked at that bonding interaction, I had to have two atomic orbitals, right? When I combined those two atomic orbitals, what did I get? I got this goofy looking picture and that goofy looking picture. What were those pictures representing? The molecular orbitals. So every time I take those two orbitals together, I'm going to generate two new molecular orbitals. Why? Because I can't create or destroy energy, more or less. So if I start with two atomic orbitals, I'm going to end with two molecular orbitals. Those molecular orbitals I can then call different things, and that's where we get sigma and sigma star, based off the type of interaction of said orbitals.
For antibonds, you say in the video the atoms are actively no interaction. What do you mean by that?
Okay, so they are actively not allowing the electrons to exist between the atoms. It's creating a node. Whereas if we talk about not a bond, right here in that middle section with my atomic orbitals, there's no interaction. Okay, there's nothing. Here, they're actively saying I'm not talking to you. Okay? So I can not talk to you, but if I not talk to my wife, that's a very different interaction. Right? Okay, that's the same kind of system here. This atomic orbital is me not talking to you. That one is me not talking to my wife. Okay? There's an intent behind that one that's significantly different. Okay? Intent is dangerous because the atoms don't have an intent. We're just saying that we're preventing that interaction. Sorry, Envy, I think I saw Oliver first.
Okay, so for the antibond, what you were saying is to that small s, the smaller the circle, the s, right? And that
Nope, nope. What's the smaller circle? This is coming from my sp2. It's my sp2 effectively inverting and pushing the electrons the other direction. Here my electrons were aligned towards my hydrogen. When I look at that antibonding interaction, what happened is it went, nope, my electrons are going to line the other direction. There's a higher probability to find the electrons away from the hydrogen than towards it. So that dotted line that I have in the antibond is the division between my hydrogen and my carbon.
So what's like the shading then? Like the shading is if it's positive or negative, right?
Why are you asking me? Yes,
Yes.
the shading is absolutely positive and negative.
So anti-bonding relates to, I guess I'm trying to understand like the sigma bonding, they were both shaded in. Anti-bonding, they were both not shaded in. So what's the difference?
No, 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 no. We left, when we looked at this interaction, okay, to get the bonding interaction, S was shaded, this one was still exactly as is. Okay, this one has the dual shading already done to it, so we don't have to change anything about this one. What's happening to get to the anti-bonding is we're saying, well, the S could have been unshaded. Okay, and if I look at that interaction where I now take the S and I overlap it with the shaded of my sp2, what's happening in this middle interaction? I don't get electrons because they're opposite phase. That's this dotted line.
So we're saying if it's either all positive or all negative, that's what happens with the S orbital.
If your orbitals match phase, they will increase. Matched phase is lower in energy. Okay? Is this matched phase? No. Because it's not matched phase, what happens? It's higher in energy. As it went higher in energy, I added a space due to that overlap that said there was zero interaction, which created this dashed line saying there's a node, a point of zero existence, because that's the canceling of my system. Okay, I don't want to draw the node in the bottom one because there isn't a node, but if I drew a dotted line in that bottom one, what happened? We increased the size at that point. Why? Because there was a positive interaction. They were both shaded. Does that help?
Yeah.
What does the asterisk mean?
Asterisk is just a way of saying antibond. Okay, so some big lessons that sort of come out of this. Okay, do we need cartoons? Arguably no. If I just want to look at the interaction between that hydrogen and that carbon, what happens? I'm going to get a bonding orbital and I'm going to get an anti-bonding orbital. My drawing gives me a tip-off as long as I've associated some of this stuff into it. Since it's a single bond, I know it's going to be a sigma bond, which means this is a sigma and this is a sigma star. So if I now want to look at this molecule, just evaluating the carbon hydrogens, how many sigmas do I have? 4. Why? There's 4 carbon hydrogen sigma bonds, which means I'm going to have 4 sigma bonding interactions. How many anti-bonding am I going to have? Also 4. 1-for-1 match. It's just, we do all of this work multiplied by 4. Eh? Or close enough to?
So for every type of molecular orbital, we have the positive and the negative, well, the bonding and the anti-bonding.
For every type of molecular orbital, you will have a bonding and an anti-bonding. Yes. Yes. Why? So, which is another fun thing. Did I talk about anything with electrons yet? Nope, there's no electrons discussed yet. Shade. Okay. Nope. How many atomic orbitals do you need to bring in to make a bond? You need 1 from each atom, which means every time you make that bond, you're generating 2 atomic orbitals. And if you bring in 2 atomic orbitals, how many molecular orbitals do you get? 2. Every single time. So if I bring in an S and an sp2, I'm going to get 2 molecular orbitals, 1 bonding, 1 anti-bonding. But if I bring in an s orbital and an s orbital, I'm going to get 2. I'm going to get a bonding and an antibonding. But what if it's sp3 and sp3? I'm going to get a bonding and an antibonding. Referencing the orbital type, 100% irrelevant. If you bring in 2 orbitals, you get 2 orbitals. Period. Okay? Why do we not talk about bringing in 3 orbitals?
Because we're just saying it's sigma.
I would argue there's one more word you should add after sigma, because the sigma is irrelevant, because we're just looking at bonds. And how many atoms are in a bond? 2. Why are we only looking at bringing in 2 orbitals? Because there's only 2 atoms ever involved in a bond. That's it. Okay? Shit, I lied. Don't worry about it yet. Okay? But at least we're coming into alignment a little bit. Okay. That was just the carbons and hydrogens. What else do I have to worry about? The carbons. Whoa, oh God. Stupid. Okay, they're all there. So I want you, at your tables, figure out what the carbon to carbon bond is going to look like. We should add a little bit more context. The carbon to carbon sigma bond is going to look like. And I don't know how to pause the recording, so for the sake of people listening at home, you're just going to get weird dead space and me mumbling to myself.
Oh my gosh. So we look at 2 of those? 2 SE2s? Yeah. These are all hybrids, right?
Nope. What was this?
S orbital?
Coming from what?
Okay.
What was this?
Also an S orbital?
Was that what it says up there?
No, wait, what do you mean?
This came from your hydrogen. What did this come from?
The carbon.
Okay.
But I
So
thought we were figuring out the hydrogens this entire time.
we've already done the hydrogen. So now we're looking at the carbons. So what's left
Carbon to
over?
carbon, yeah.
So now we've got a couple questions to address. Number 1, you said, how do I know the hybridization?
Yeah.
Okay. And you guys went to SP2, which was cool, but you didn't actually answer your question.
Yeah.
How do you know it's SP2? And not just because I told you, you should be able to know why it's SP2.
Yeah.
How many groups of electrons around the carbon?
Because each carbon forms sigma.
So this one, well, I'm just going to draw it on here and erase it later. So when we look at that carbon, we go back to Lewis structure. Lewis structure is based off of a square. So if we're looking at this, this is what we're drawing for our carbon. Do I have electrons here? Do I have electrons here?
Yeah.
Do I have electrons here? Do I have electrons here? How many of those were electrons?
1, 2, 3. Wait. Yeah. What did it not before?
So you're saying how many bonds. I did not
8,
ask how many bonds. I didn't say how many electrons. I just said, are there electrons?
Yeah.
Are there electrons on this face of that
No.
square? Are there electrons on this face?
Yeah.
Are there electrons on this face?
Yes.
Are there electrons on this face?
Yes.
How many faces had electrons?
3.
How many regions of electrons are there? 3.
3.
And if I have 3 regions of electrons, what does that mean my shape is?
Trigonal.
What does that mean by hybridization is?
SP3?
SP2. Why? I need 3 regions, right? I need 3 equivalent regions. If I do SP3, what I'm going to do is take all of those and put them all together. How many atomic orbitals is that?
8? Wait. If there's 2 orbitals.
I don't care how many electrons. How many orbitals is SPPP? What is S? An orbital. What is P? An orbital. So how many orbitals is that?
4.
4. Which means if I do that, how many regions of electrons am I going to get?
4.
4. Did I want 4?
No, you want 3. So it would just be SP2. Because there's 3 P's.
So that's how you get to that hybridization. So if we're going to evaluate what you did here, this was sp2, that was sp2, that was sp2, that was sp2. What's left over for this carbon for this area? Well, we used 2 sp2s for our hydrogens. I've got an sp2 left over, and I have a p left over. Conveniently, I have 2 bonds I have to address.
Oh, because we just
I said, I want you to draw out the sigma bond, right? Which means what orbital must you use? To draw out the sigma bond, you have to use only one of them. A p bond generates from pi orbitals, or p orbitals. If I said sigma, it needs to be S type. It has to have an S in it. sp2 is what's used. So what orbitals are you bringing together for this? The sp2s. So let's talk through it. Okay, we're talking about the carbon-carbon sigma bond. What orbitals am I talking about bringing in from each of those carbons? Okay, and that is a tough question to address. So let's go back and consider what orbitals our carbon had. Okay, let's just pick one of our carbons for the moment. I don't know how to color it. Does yellow work? Does that kind of work? Oh, that. So judgmental. Is that better? Can we get away with that? It's calling that yellow? Okay, so if I'm going to look at that as my yellow carbon, I want to know what orbitals are left for me to be able to talk about making a connection with the other carbon. Okay, so I started with my 4 atomic orbitals, or my 4 hybridized orbitals. Those are allowed to be used for my molecular orbitals. I used one of the sp2s to bond to a hydrogen, right? That's the drawing that we just drew. That's our molecular orbital system. So one of those sp2s is gone. Didn't I have another hydrogen? What orbital did I use for that other hydrogen? sp2, which leaves me with 2 orbitals that I can choose from to make the sigma bond between these 2 carbons. It has to be the sp2 because it has an S. Okay? We're playing a little bit fast and loose with the rules because the definition of what makes a sigma bond versus a pi bond, we haven't fully addressed in class. That's in the lecture videos. Okay? So we defined that our sigma bond has to be S-type, which means the orbital that we're going to bring in from that S1, I think I'm going to regret coloring it in yellow. Is that okay? Okay. That one's going to be shaded like that. It could just as easily be shaded the other direction. Okay? Both of those are fair game. What about the other carbon? What is it bringing in? It's also going to be the sp2. It's going to have the exact same checklist of all of those orbitals that we went through and did. Okay, so it's also going to bring in an sp2. There's our same deal. Okay, and again, shading could be opposite. So I now want to bring those close enough to each other that the orbitals interact. Okay, as drawn, it's a little bit easier to see. What's going to happen to the overlap? Is that constructive or destructive? Constructive, which means I should see a larger probability of finding the electrons between the carbons. We show that larger probability by expanding the space a little bit between them. So if we were going to go through and draw in our carbon nuclei, pretend, okay, and we're going to draw our shape, what happens is I'm going to see a larger probability of seeing the electrons in there. I don't get to lose the little tail ends, so those are also left out there. What does that mean? Well, since I have a larger probability of finding electrons between the atoms, this looks like a bonding interaction. What kind of interaction was it? It's sigma. Why was it sigma? We can run that they were S-type orbitals. We could also run, again, jumping ahead of ourselves a little bit, that it's a direct overlap of those orbitals. That direct overlap makes them sigma. So we could call that a sigma bond. Or a sigma bonding. We shouldn't be calling it bond, sigma bonding. It's a description of the orbital type. Did they have to overlap in alignment? No. There's an equal probability. Stop giving me the eraser. There's an equal probability that it comes into alignment like this. Now, when I bring them close to each other, what happens? Do I get that same constructive overlap? No, one is shaded, one's unshaded. That cancels out, which means in that space where they overlap, I would generate a node. I can't put electrons there. I've now decreased the probability of finding the electrons in that space. Okay? What happens to the rest of it? Well, the rest of it effectively remains unchanged, and you can get more nuanced behind that, and quite frankly, maybe you should, but I don't know it well enough. So we'll go through, call that shaded. This is unshaded, and then that part was shaded. So I brought in 2 atomic orbitals. How many molecular orbitals did I make? 2. One was that bonding one at the bottom. What did I make at the top? Antibonding. And I could go through and cartoon diagram it, and there we go. We could say that's my sigma antibond. So if we were running a full tally of this, sigma bond and sigma antibonding, okay, each of the carbons had, or with the hydrogens, generated a bonding and antibonding. So we had 4 sigma bonds and 4 antibonds, right? I don't know why I put a star on that one, but that's good enough. For the carbon to carbon sigma bond, what do I get? I get 1 sigma and 1 sigma antibond. So that's starting to describe my overall molecular orbital diagram. Ish? Okay. Not that way. Can I actually scroll? Before we do that. This is kind of cool. I hope the scrolling actually works. We have one last thing that we have to discuss, right? What's the last thing we have to discuss? What's happening with that P? Okay, we'll come back to resonance too. Okay. What's left over with that P? Okay, I haven't explained anything about it, but if we go through and look at the carbons, we have 4 bonds. We've explained for our carbon 3 bonds. There has to be a 4th bond. I have to have that extra line, right? So what's going on with that extra line? What orbital must I use for that extra line? I have to use a P. Why do I have to use the P? The sp2s are already gone. Okay, so now what goes through, reverse direction, my carbon atomic orbital, here's my P. What's the other carbon using? That's also another P. Okay, my carbon atomic orbital. Shaded, shaded, right? Okay, if I bring those into alignment, do they ever directly overlap? Okay? You say, well, couldn't I overlap it in the system? And it's hard for me to draw this. Where they overlap. Well, that looks like a direct overlap. Isn't that possible? Well, what we have to remember is that we aren't just looking at those p orbitals. Those p orbitals are also in conjunction with our sp2. There's my sigma overlap. Once it is overlapped, what happens? The atoms can't get any closer, which means, do the p orbitals ever get close enough to directly overlap? No, they don't. Okay? And this is where we were talking about the end-ish of the last lecture with the pens. The pens do a pretty decent job of representing our p orbitals, and a little out of shape, but you could do the shading of the color on one end and unshaded on the other-ish. You've got your p orbitals. Okay, so when we talk about the bond, they never get close enough where they can touch. That doesn't happen. They get about there. Okay, well, if the orbitals never overlap, should we ever get a bond? No. The only way you get bonds is when orbitals overlap. Okay? So this theory of hybridization and then combining it with how these orbitals can potentially interact with each other has a giant gaping hole in it. That giant gaping hole is filled when we start to actually look at what's happening here. What are these orbitals representing? Our electrons and the energy of our electrons, and ultimately related to where they're at, location, direction, all of that fun stuff. And what we end up finding is that when we drill down into electron motion and study quantum physics of it, is that electrons have an ability to tunnel through spaces they're not allowed to exist. Said another way, as long as my p orbitals are close enough to each other, the electron can tunnel from one side to the other. It can just appear. You can do the mathematics for it. Okay, if you're lucky enough to be a chemistry major, you'll probably do the mathematics for it in a physical chemistry class. Okay, and you'll probably be like, why the hell am I doing this? Because this makes no sense to me. And that's because you didn't pay enough attention in OChem. Okay, or you decided it wasn't worth your time, and I get it. Okay, but that's what's happening. So we don't see that tunneling effect when these things are moving around all over the place. But once the sigma bond has locked those two structures next to each other, now they're close enough. You go, oh yeah, you're kind of close. I'm just going to jump. Boop, I'm there. Okay? So it becomes kind of a different system that now we don't directly overlap, but I'm still allowed to make that jump. Which then means, yes, the electron over here can be over here. How do I want to represent that? Well, they're now in phase with each other because of the shading is aligned that way, which sort of turns into something, depending on how you want to look at it. This is usually what your textbook shows, is something like this. Okay, and we could draw our nuclei in there too. Okay, that phase for your p orbital line is still there, that node, but now our electrons can be whoop all the way up the top or all the way on the bottom. Our electrons have more space, that's lower energy, happy. Okay. When we get into resonance, I would argue a better representation for it would be this. They're in phase, they're close enough, they can jump. Oh, happy day. Did they directly overlap? Nope, so I can't call them a sigma bond or sigma bonding. I need a new name. I'm going to call it pi because what orbitals did I use to make the pi interaction? P orbitals. That's where the name comes from. Maybe. I actually don't know. Okay. But did the orbitals have to come in alignment? Remember, these phases are constantly all over the place. They don't have to align like this. What else could they have been? And conveniently enough, I have some space way above on the page, so we'll just draw it way up there. Okay, we go up. Let's leave the first one alone because, you know, the first one's always nice, right? For all the first childs out there. Okay. Maybe there's some first children out there, and that's why they laughed. Okay. The other one didn't come into alignment. Can the electron jump now? No, so now the electron is locked on that one spot. Okay? That makes it less happy. It's not allowed to move around, which means it's a higher energy state. Because the electron is set with another node, it can't make that jump anymore. That's now higher in energy. And since it's higher in energy, I would call that antibonding. But what kind of interaction am I trying to draw? Indirect, and an indirect overlap is pi. So this is now pi star. So if I wanted to look at that second bond in my double bond, this is my molecular orbital diagram. Okay, this gets a bit dodgy, and we'll come back to that in a second. This is my molecular orbital diagram, including those. What were the extra pieces on the sides? What is all this? Those are our atomic orbitals that are helping us to understand how we got to the molecular orbitals. Do we need them? No. Do you need them? I don't know. You decide. Okay? So if we now summarize all of this information into one giant thing, which was now what are all our orbitals that we're dealing with, okay? What did we generate down here at this part of the page? We generated one pi and one anti-pi. So I would also have a pi anti and a pi, one of each. So in sum total, I have 5 sigma antibonding, 5 sigma bonding, 1 pi antibonding, and 1 pi bonding. How many total molecular orbitals do I have for this compound? 6 is an interesting way to count that. It's not wrong, but I didn't count it that way. I would have gone 5, 5 to 10, and then 1 and 2. Okay, and we got 12. So there's 12 molecular orbitals for this. Okay, could I have figured that out really early on? How many bonds are in my Lewis structure? 6. And for every bonding interaction, I get an antibonding interaction, which means if I drew out this structure, right away I could go through and say there are 12 molecular orbitals because I see 6 bonds. Of those 12 molecular orbitals, 6 of them are bonding, 6 of them are antibonding. Of those 12 molecular orbitals, because I see that I have a double bond, and I know double bonds is a nonsense statement, and a double bond is really a combination of a sigma and a pi, I know one of those bonding interactions is a pi bond, and one of them is a pi antibond. And if I really wanted to get fancy, not that way, actually I could have gone that way, I could go through and I could say the molecular orbital diagram for this structure would be 5 sigma bonds, 5 sigma antibonds, 5, that's not 5, that's 1 pi, and 1 pi antibond. Do I want to bring electrons into this? I could. Why not? Let's get exciting. Okay. We're showing these as lines. These are supposed to be 5. 1, 2, 3, 4, 5. Okay. Officially, I would do it for the 5 sigma, but I'm not even going to worry about that. Okay. Why not? How many electrons do I need to draw into my molecular orbital diagram? How did you know it was 12? Who said 12? You have 6 bonds, and each line represents 2 electrons, so I need 12 electrons. So we can start drawing. Ready? All together now, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Damn, I'm out of spots. Okay, I accept. 11, 12. That's now my molecular orbital diagram. Well, you didn't define what the energies were for the sigma. Do you want to? No, thank you. Yes, take a different class. Okay, that's all you would need to really be able to do. Kind of, sort of. I promised resonance, and since I promised resonance, we're going to take a look at quick run here. The structure that we just drew isn't really going to have good resonance, so we're not going to worry about that one. But let's go ahead and draw another structure here. Okay, well that carbon will imply hydrogen, so let's not worry about the hydrogens. And we could do a couple things. I can leave it as one carbon. Yeah, let's leave it as one carbon. And we're going to put a positive charge right there on that one carbon. What is the hybridization of this carbon? Remember implied hydrogen. Oh, SP2. What is the hybridization of that carbon? SP2. What is the hybridization of that carbon? SP2. What do all of them have left over? A p orbital. Okay, for the first two carbons, you're using that p orbital to make that pi bond. For that last carbon, that p orbital is actually going to be empty. How do you know it's going to be empty? It says positive charge. That's why there's not electrons there. Okay? So that more or less gets us our molecular orbital diagram kind of half-assed. Resonance. When I do resonance, what can I do? I can move electrons. What electrons can I move? I can move bonds. Which bonds? Pi bonds. How can I move pi bonds? I can move them to an atom or to a bond. Generally, moving bonds to atoms isn't going to give you new or better-ish resonance structures. So if you're going to move a bond, I would generally say to move bond to bond. Okay? So I could go bond to bond. What happens with my structure? The other carbon on the other side becomes positively charged. So do I have resonance? Yes. Why was I allowed to do this resonance? That's a good answer. It's now got two positive charges. So now that one's SP. Okay. It has nothing to do with them being the same resonance. What's allowing the electrons to move? Which bond? The pi bond. What orbital? The p orbital. What is left over on an sp2 hybrid atom? A p. What is left over on an sp hybrid atom? P. Which means to do resonance, guess what your atom needs to have? A p orbital. If it has it, guess what can happen? Resonance. So why is resonance working the way it's working? Okay, we haven't done this. We're going to play with some weird stuff here. If we take a look at this structure as drawn, this black structure is flat, two-dimensional. Okay, all of those atoms are in the same plane. And that sp carbon's killing me, but I had to add that just to break you. So I'm going to take it back to that. Okay, so now all of our atoms are in the exact same plane. But what I'm going to do is I'm going to take that top carbon, that point, and what I'm going to do is I'm going to take it at top of the plane and I'm going to pull it down. Do you work out? All right, stupid. Okay, you pull that carbon down. So now that carbon is dead in the middle in front of you. These other carbons are actually going to be going kind of back away from you, right? So we could show them as dashed. Why on God's green earth would I do that? Why do I want to show 3D? To make that pi bond, what did I need? To make that pi bond, what did I need? Not electrons. I don't care about electrons. Yes, I needed them, but there's something else more relevant. Yeah. I needed p orbitals. I need a little bit lower on the screen. Where are the p orbitals on these carbons? They must be perpendicular to the plane of those bonds. They can't be in the same plane because then your orbitals are overlapping the bonds. That's bad. So it has to be, boom, right there coming out of the plane. Can I draw a good p orbital coming out of the plane at you? No. Can you? So stop judging. We go over here, right? And then what did I say I wanted to do? Grab that top carbon and pull it out. So what's neat about pulling this out? What have I just done? If I'm going to draw my p orbitals now on that new structure, why did you lock? Why did you go away? There's that p orbital. There's that p orbital. They're now very clearly in the plane of the structure. That last carbon, let's call it our red carbon. That's a C, I promise. We said was sp2. Where's its p orbital? What's neat about this? Can I draw in the phases where they're all in alignment? And by drawing them all in alignment, what could my electron do? It could jump from here to there. Like, duh, it could do that anyway. That was the double bond. But since that other p orbital's there, what else could it do? It could jump to that one, as long as it's in that plane. And it wants to be in that plane because what's happening? Resonance. That's why resonance exists, is your p orbitals overlap. What happens if I rotate that bond? What would happen to that p orbital that's now up here? Depends, and I know we're done. P orbital, p orbital. This is a sigma bond, right? What happens if I rotate that bond? Say again? They're perpendicular. Why does that matter? Why can't the electrons jump anymore? They're not overlapping. Okay? If I go back, boom, now they're in alignment. Now I can do resonance. Now I can do that happy electron dance. It can jump all the way across. So as long as I have those p orbitals left over on each of those carbons, I can do resonance. Go back to all the practice on resonance you've done. Look at where they're at and identify the hybridization of any atom that was affected by your resonance drawings. And you know what's going to be neat in all of those? Every single one of those atoms will have at least one p orbital, unhybridized. Every single one of them. Molecular orbital theory, this hand wavy, we just make some stuff up with hybridization and you draw some shapes, explains why resonance can exist. That's pretty cool. Thank you. We're done. I know you wanted to talk about resonance there at the end. Would that get you close enough?